I'm going to show you guys how to analyze the time complexity of an algorithm. This video assumes you already have theoretical knowledge about big O notations. You should be familiar with time complexities such as linear, constant, logarithmic, quadratic, and exponential. Click this link here to watch a video that goes over those basic time complexities, or click the link in the description. If you already know those time complexities, then keep watching. This video is going to show you how to apply that knowledge more practically, so that way when you're analyzing an algorithm, you can properly determine the time complexity of that algorithm based on the code. Many algorithms are not simply linear or quadratic, but there's some combination of both. It's one of the most fundamental skills from those who just know how to write basic coding and those who know how to write the best code. As a quick recap, let's get clear on some definitions. An algorithm is simply step-by-step instructions. It's code. Any kind of code is an algorithm. And time complexity refers to the efficiency of that algorithm or the code in relation to the input. And you should already know about this. If you don't, click the link in the description to watch that video first. And one more thing, you should know these time complexities of these various operations. Depending on your programming language, it may be different, but for the most part, they're going to be the same no matter what programming language you use. Pause the video, review this stuff. You should understand why all these lines of code have a time complexity that is commented right after it. Google it, use ChatGPT, walk through all of this and make sure you understand it. I highly recommend it. So to analyze the time complexity, what I like to do is for each line of code, I determine what the time complexity of that line of code is in isolation to start. For example, res equals an empty string. It's a constant operation. This one, however, we're iterating through the length of the first string in our array. So let's say n equals length of strings, and we'll say m equals length of the first string. So with this definition in mind, then we're going to say that this is O of m because we're doing a for loop through the entire length of n. And then we say for s in strings, we're iterating through this whole array. That's going to be a big O of n. This is a constant operation. This is constant. This is constant. So these are all constant operations. So this is going to be constant. So I'm going to clean it up a little bit. Maybe that's easier to read. So I'll do it like this. And then when we return the res variable, that's a constant operation as well. So if we look at res, it is not nested within this loop, but it's nested within this loop. And then when we do big O notation, we want to think in the worst case scenario. And so in the worst case scenario, res is going to be the size of m. And so this is going to be an O of m operation. And then at the end, this is a constant operation. So now that we've defined the time complexities of each line of code, now we can combine all the time complexities at the end. So the way we can do that is if I go down here, we're going to start with big O. This is a constant operation, so I'll do 1 plus an O of m operation, so I'll do plus m. And then we have n. N is nested within m, so it's not going to be m plus n, it's going to be m times n, because we're going to do this n loop m times. And then within the n loop, we are going to do this constant operation n times. And whenever you do something within a loop, you're normally going to multiply when you combine the variables when crafting your big O notation for the entire algorithm. So that's n. And then within here, this statement will only happen once at most, because once this happens, the function ends. So it's just going to be a +1. After all that, we can kind of group this together. So this, all of this is going to represent all of this. So we go m times n times 1 times 1. We're also going to do this O of m operation m times. So that's going to be m squared, or we could just say m times n. All right, so I'll group those together just so it's a little easy to read. So again, that's that first loop that we looked into. This is going to be this times this. At the very end, we're also going to return something, so we can do +1. So now we got our big O time complexity for this algorithm, and assuming you already know big O notation, you know the basics, you should know that we can drop constants. So we don't need to worry about the constants, so let's get rid of them. And so now we just have m times n plus m times m. And m times m can be reduced to m squared. So this is basically m times n plus m squared. And we also want to drop the non-dominance, meaning, you know, if m times n is always bigger than m squared, then we would drop this. But it's not necessarily. This could be bigger, or this could be bigger. We don't actually know, because let's say, for example, let's say m equals 1 million, and let's say n equals 10. So yeah, 1 million times 10, that's going to be 10 million. 1 million squared is going to be like 1 trillion or something, right? So 1 billion is definitely bigger than 10 million. But on the flip side, if m is only 10 and n is 1 million, 1 million times 10 is 10 million. But 10 squared is 100. This time, this would be bigger. So we don't actually know which of these factors is going to be bigger, so we keep them both. And so this would be the final time complexity of this entire algorithm. And we figure that out by determining what the time complexity of each individual line of code is. And then we combined it at the end to calculate the time complexity for the entire algorithm. So let me actually first show you how we would make this algorithm more efficient. So what we could do is, instead of making this a string, we'll make this an array. Still constant operation. This is the same. This is the same. What we want to do though, instead of adding this character to the end of the string, we're going to append the character. So now this becomes a constant operation. And then when we return it though, we need to return it as a string. Basically what we're doing now is this append operation is constant. And then when we return it, it's going to make this a linear operation. Let's recalculate the time complexity for this whole algorithm and let's see how it improved it. So instead of this, we're just going to skip this constant, right? Because we kind of already know it's not going to be included. We'll do m times n, which is these two being combined. And here you may be tempted to do times n again because it happens within this loop. But the thing to understand is that this only happens one time at most, because when this happens, we're returning from the function, so the function ends. So actually, it's just going to look like that. It's going to be m times n, and then we might do a single more linear operation, okay? But then after that, it's done, so we're not going to include it for each iteration of the loop. If that doesn't happen, then this linear operation would happen, which again, you know, we drop the constant, so we don't have to worry about that. After this is all finished, we're going to return and join the strings together. And so that's just another plus n. That can be simplified to 2n. We're potentially doing this twice, except it's only possible for it to happen once because it's in a return statement. So we can remove that. Even if it did happen twice, we would remove the constant anyways. And then this time we do drop the non-dominance. And since n only happens after this happens, there's no way that n could be greater than m times n. So we can drop the non-dominant. And so with this optimized algorithm, by using an array or a list instead of a string, we've made the time complexity m times n instead. Next, let's go over this example. So when we sort nums, that's going to be an O of n times log n. Typically, that's going to be the time complexity of a sorting function. This is constant. When we loop through the length of nums, we'll say n equals the length of nums. This for loop is big O of n. This is constant. This one's constant. This is also constant. We're just assigning variable names. Before I get into what this is, let's go inside. If we look at all of this, like we're just accessing an array, we're doing some math, we're comparing less than, greater than. These are all constant operations. I'm just gonna group that as all constant. This is a constant operation. But let's say nums equals, it's just a bunch of numbers like that. And then the indexes of those numbers, put them down here. In our for loop, I will be iterating through all of these numbers, right? I is going to start out at 0, and then it's going to go all the way up to the length of nums, which this length is 10, minus 2 is 8, so it's going to go all the way up to 8. If we look at how we initialize left and right, left starts out as I plus 1. So left is going to start 1, and then the right variable is going to start at the length of nums minus 1. So if this length is 10, it'll start out at the 9th index. So this will be right. And in this while loop, we're saying while left is less than right. So right now, left being 1, it is less than right, which is 10. We're going to be doing a bunch of comparisons. And depending on these conditionals, we're either going to add 1 to left or subtract 1 from left. We're also going to do that in these loops as well. We're either going to increase left by 1 or decrease right by 1. And then at the end, we will also increase left by 1 and decrease right by 1. This loop is going to break when left is no longer less than right. So even though it's a while loop, we can only do so many operations. So either left is going to be increased by 1 or right is going to be decreased by 1. It's going to keep on doing that until they meet. And so the maximum number of operations that we can move left forward or right backwards, or some combination of doing both of those operations, is the size of this whole subarray, which is to the the right of I. Sometimes you can't just look at the code and see what length it iterates over. You have to visualize the algorithm and understand what it's doing. And so in this case scenario, then let's say on the next iteration, I goes to the next index. When we recalculate what left is going to be I plus 1. So left is going to start at 2. Right starts at the very end again, though. And they shrink together. And then on the next I iteration, I is going to move forward. Left is going to come here. And then again, they shrink together. Okay, so left comes forward, right comes backward until they overlap. And then the loop breaks and we don't do any more operations. As I goes through the array, the area in which left and right shrink is going to get smaller and smaller. But overall, if we do the calculations, basically left and right is going to move on average. If we look at the average length, it's going to move as I moves forward. On average, it's going to move through, it's going to do n divided by 2 operations. It's going to move around half this length. Because in the beginning, it's going to be the full length, or almost the full length, and then a little less, and then a little less, and a little less, right? And then if we average it out, like if we do, because if this is 9 iterations, this is 8, 7, and then 6, and then 5, 4. If we add all those up, 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, and then we divide it by 9, that's going to give us like 4.5 or something like that. And that's going to be our average. So if I do 1 plus 2, actually, let's just keep it simpler and go backwards. We do 9 iterations, 8, 7, 6, 5, 4, 3, 2, 1, divided by 9. Right, that's 5. So it's roughly n divided by 2. Again, we can drop the constant and it's roughly linear. That's why this whole loop here is going to be big O of n. And then, so this whole thing is linear. And then we do this linear operation n times. And then we also have this n times log n function. So if I get rid of the constants, we're not going to add that to our final time complexity. The time complexity of this entire algorithm is n times log n, which is this, plus n times n. And we're going to do it n times. So it's going to be n times n. We can simplify that to n squared. If we look at this, n times log n is always going to be less than n squared. Because if n is 100 and log n, so then log n would be 10. 100 times 10 is 1,000. 100 times 100 is 10,000 though, which is more. N is always bigger than log n, so we can remove that. That is the final time complexity of this function, which basically iterates through the length of an array and then uses a 2-pointer method on the remaining length of the array that has not been searched yet to find all 3 pairs of numbers that sum to 0. If I do it with these inputs, the output is going to be all these triplets of numbers, which they all sum to 0, right? 3 plus -1 plus -2 is 0, so they all add up to 0. So here's another example. This resembles like a Fibonacci sequence, except we have this random loop in here. So first of all, this is constant operation. This is also a constant operation when we evaluate x to be 0. As we iterate through the length of n, that's obviously linear as an O of n. That's going to be n as well. If you are familiar with the time complexities mentioned in the description of this video, we're splitting into 2 different call stacks for each recursive call. So if we try and combine everything at the end here, we can drop the constants, obviously. We're doing this linear operation a linear amount of times. So that's going to be n squared. So since we're doing n squared operations within each call stack, and there are 2 to the n call stacks, then the time complexity is going to be n to the power of 2 times 2 to the power of n. That's another example. Here's the final algorithm that I'll go over the time complexity of. Here is the problem taken from LeetCode. This is the description. For the sake of this video, I am going quick. Definitely make sure you're pausing to make sure you can process the information properly so you can keep up with me. This video has edits. I've already done some pre-planning, and so you're not going to be able to keep up more than likely by just watching the video if you're a beginner and this is newer to you. So let's just go step by step. If you don't know Python, basically what a default dictionary is, default dict, is if I did this line of code right now, the dictionary, it would look like this. Even though I didn't insert A into the dictionary yet and I'm just accessing and I'm trying to append it, the default dictionary, if we try and access a key that does not exist yet, it will create that key with a value of an empty list. So just some quick context. This is a constant operation. this function, let's not even look at this function yet in terms of the time complexity, because this function is not called yet. So we don't know what inputs it's going to be called with. Now, I tried to make the code descriptive, so maybe you can guess, but let's just wait till we get to where the function is actually being called before we try and calculate the time complexity of that. We could say n equals length of s in terms of like our variable definitions for our big O notation, m equals length of t. Instead of n and m, we're going to use s and t to represent the length of s and the length of t. This is going to iterate through the length of t. So that's big O of t. This is going to iterate through the length of t as well, because we're going from one index after I all the way to the end. So worst case scenario, that's going to be about the size of t. This is a constant operation, so I won't bother. The biggest substring that we're going to create is going to be the size of t. So we're going to say big O of t. And then here, if it doesn't exist already, create that list and then append that substring that we created here to the array. This is a constant operation. I'll just write it real quick. This is obviously constant. Okay, so now let's look at this. We're going through the length of s. So let's say the big O of this loop is big O of s. This is very similar. We're actually doing the exact same thing as we did up here. So this is going to be big O of s again. And then here, s substring, at most, this is going to be the full size of s. We're going to have to recreate an entire new string. It's going to be the full length of s. So this will be an O of s operation. This is constant. Now, if we go through here, for t substring and substrings, now this one's a little more tricky. And so this is where it takes us like understanding kind of how the algorithm works and like how the code progresses or how the algorithm progresses. So if we look at t substrings, that is taken from this dictionary, and basically we were appending substrings to it, okay? And we're doing that, if we look at this dictionary, basically we're grouping substrings by length. So for the length of 1, we have a bunch of substrings. For the length of 2, we have a bunch of substrings length 2. For the length 3, we have a bunch of substrings of length 3. And so if we think about it, again, this would maybe take understanding this algorithm a little more to understand what the question is, to be able to think this through. And maybe I can even draw it out to make it a little more simple. You know, let's say we have a substring that's A, B, C, D, E, F, G, right? If it's of length 1, there's 1, 2, 3, 4, 5, 6, 7 possible substrings. If it's a length 2, 1, 2, 3, 4, 5, 6. And we can roughly see that the number of substrings is at worst case scenario, and on average probably, it's going to be about the full length of the string. Now this string that I'm referring to is going to be S or T. That's the full string, and then we're creating substrings out of that. And this is where we're creating the substrings, and then we're adding those substrings to a dictionary where if the key is 1, the key of 1 is going to be equal to a value that contains like the letter A. If we're looking at it, let's pretend this is the string, then B and C. So all that to say, I'm trying to paint the picture of why this is going to be big O of T, because when we create those substrings and we add it to the dictionary, the number of substrings for each length is going to be about the size of T. So if we look at this function definition, the T substring, we can see that we iterate through the length of T. So we can say this is big O of T. And then this is constant, this is constant. Okay, so we can say that this is big O of T. Okay, so now we can combine the time complexities. T O of T operation happens T times, which also happens T times, which is going to be T to the power of 3. So now we come here, and so this is going to happen after this block of code. They're separate, so we're just gonna do an addition to add them. This first loop is O of S, because we're iterating through the full length of S. So we're going to say S, and then this for loop happens within here. So we do this S operation S times, so that's going to be S squared. And then in here, we're creating this substring, which is potentially the full size of S itself as well. Since we're doing this S operation S times, which is happening S times, this is S to the power of 3. Okay, very similar to what already happened up here. But now we have another operation. What we're going to do here, we're going to separate it out, and we're going to do S squared to count for these two loops. And so this T operation is going to happen S squared times, because it's happening within these two loops. loops. So we're gonna multiply it by t. In this t loop, we're doing this operation, which is also O of t. So this is gonna be t squared, just to kind of separate what we've created. So we've got this, which is gonna include these two loops, and then this loop, and also this loop inside here, right? So that's why this is s squared times t squared. S to the power of 3, that's going to include those three operations. And then t to the power of 3 is going to include this. So that's how I would calculate the time complexity of this problem. And notice, for me to understand, like, how do I figure out the time complexity of this? It doesn't directly correlate to S or T by just looking at it. We don't really know. Yeah, it's a little more complex, but you need to be able to understand how the algorithm works to be able to determine that. None of these are dominant, because if t was way bigger than s, then t to the power of 3 is going to be bigger than all of these operations. We don't know what the dominant is, because if t is way bigger, this would be the biggest, this would be dominant. If s was way bigger, this would be the biggest. But if they're about the same size, then this is the biggest. This final example is actually from a student in my program. They asked me for help in understanding the time complexity of this algorithm. The original code was a little less readable, so I tried to make it a little more readable for this video. I hope that video was helpful in helping you learn how to analyze the time complexity of an algorithm, and giving you practical examples of how to look at the code in trying to determine what the time complexity is. I gave some pretty hard examples in some of them. Some examples are obviously way harder, but if you're just getting started out and trying to analyze the time and space complexity, I think these examples will definitely give you a good head start in heading in the right direction and kind of knowing how to think to be able to get proficient. If you're looking to fast track yourself into the software engineering industry, there's a link in the description where you can book a call with me. We can talk and we can see if you are a good fit for my program. So if you're really serious about getting the skills of becoming a valuable, skilled software engineer, and you want to start a career in software engineering, then it's probably a good idea for you to check out the program. Otherwise, I hope you keep enjoying my free content, and best of luck.